Designing an unfed half-wave antenna for 80 meter through 6 meter is an excellent homebrew project because a half wavelength wire on 80 meter is roughly a full wavelength on 40 meter, 1.5 wavelength on 30 meter, and so on. It naturally resonates on the harmonic bands. However, the impedance at the end of a half-wave wire is extremely high, typically between 2000 and 3000 ohms. To bring this down to the 50 ohms expected by your transceiver, you will need a broadband matching transformer. Getting this setup to perform well all the way up to 6 meter requires careful attention to the transformer's stray capacitance. The 49:1 impedance transformer UNUN, the heart of the unfed half-wave antenna, is the transformer. A 49:1 ratio transforms a 2450 ohms impedance down to 50 ohms. If you are pushing this with a 100 watt, a single FT24043 ferrite toroid is the standard choice. It handles 100 watt SSP or CW comfortably without saturating. Winding ratio. You need a 1:7 turns ratio. The impedance transformation is the square of the turns ratio. 7 squared is equal to 49. Turns. Use 2 primary turns and 14 secondary turns. You can use 1.2 mm 18 AWG enameled copper wire. The crossover. Wind 7 turns, cross the wire over the toroid to the opposite side and wind the remaining 7 turns. This reduces stray capacitance, which is critical for making the antenna usable on 10 meter and 6 meter. The high voltage compensation capacitor. To flatten the SWR on the higher frequency bands, 15 meter, 10 meter, and especially 6 meter, you must add a capacitor across the primary winding in parallel with the coaxial connector. Value typically 100 to 150 picofarads. It must be a high voltage ceramic or silver mica capacitor rated for at least 3 kilovolts. Even at 100 watts, the RF voltages at the feed point are high enough to fry standard capacitor. The radiating wire. The fundamental length of a half-wave wire is calculated using the standard formula where f is your target frequency in megahertz. Length in meters is equal to 142.5 by frequency. Length in feet is equal to 468 by frequency. For the lower end of the 80 meter band, that is 3.55 megahertz, the theoretical length is roughly 40.1 meters or 131.8 feet. Cut the wire about 1 meter longer than calculated. You will fold the end back on itself to tune the antenna for the lowest SWR on 80 meter. Because the higher bands are harmonics, tuning the base frequency generally brings the rest of the bands into alignment. Even though it is unfed, the antenna still requires a return path for the RF currents. Counterpoise. The shield of your coaxial cable naturally acts as a counterpoise. Choking. To prevent common mode RF current from traveling all the way back into your shack and causing interference, install a 1:1 common mode current choke on the coax. Placement. Place the choke approximately 0.05 wavelengths, roughly 4 meters, away from the transformer. This allows that short section of coax shield to act as the counterpoise while blocking RF from coming further down the line. You may find that tuning the wire perfectly for 80 meter makes the 40 meter, 20 meter and 10 meter bands resonate slightly too high in frequency. This is due to the end effect of the wire. To fix this, you can insert a small compensation coil about 110 microhenries, roughly 2 to 3 meters from the transformer end of the wire. This coil electrically lengthens the wire for 80 meter but acts as an RF choke for higher frequencies, allowing you to tune 80 meter independently of the harmonic bands. Here is a straightforward practical guide to building a highly effective 1:1 common mode choke capable of handling 100 watts across the 80 to 60 meter bands. The core material for a broadband HF choke covering 80 meter to 6 meter, a single FT240-43 2.4 inch diameter mix 43 ferrite is an excellent choice. It provides a good balance of high choking impedance across those specific bands without saturating or overheating under 100 watts of power. You will wind the actual coaxial cable around the toroid. RG58, the standard affordable choice. It handles the power easily, though it can be somewhat stiff to wind tightly around the core. RG316 or RG400 is recommended. These are Teflon dielectric coax cables. They are much thinner, highly flexible, handle heat exceptionally well, and allow for a very neat, tight wind on the toroid. Winding the choke, the W1JR method. To maintain good choking performance on the higher bands, 10 meter and 6 meter, you must minimize stray capacitance between the input and output ends of the coax. The W1JR crossover method is the standard way to achieve this. You need 12 to 14 turns in total. Pass the coax through the core and wind 6 to 7 turns, keeping them snug and adjacent to one another. The crossover, take the cable directly across the open diameter of the toroid to the opposite side. Second half, wind the remaining 6 or 7 turns, ensuring you continue winding in the same direction through the core. Result, your input and output coax connectors will end up on opposite sides of the toroid, keeping the hot and cold ends physically separate. Mount the finished toroid in a weatherproof PVC or ABS junction box. Solder the ends of the coax to SO239 chassis connector on either end of the box. For an unfed half-wave antenna, do not place the choke directly at the 49:1 transformer. The system needs a short length of the coax shield to act as a counterpoise to complete the circuit. Place the choke about 3 to 4 meters down the coax line from the transformer. Everything past the choke, heading towards your radio, will be shielded from the common mode current.